Hi everybody, welcome back to our topics in physics. So today what we want to talk about are some really cool applications of this idea of orbits and potential energy. So we're going to combine some of the ideas we've already talked about. So some of the ideas about gravitational potential energy and some of the ideas about what an orbit looks like, and look at some kind of neat ideas of this. So one of the things, again, the spoiler alert, we're looking at some black holes today, which again, those things that everybody's heard about, but most people don't really know what the heck they are. So we're going to talk about those a little bit today. But first, let's start with just a satellite. And again, remember what a satellite is. It's an object that's orbiting another one. And what that means is that it's traveling around it in an ellipse or a circle, and the only force acting on it is gravity. So let's examine an object of mass m, little m here, in circular orbit or at some radius r around another planet of mass big M, and it's traveling, of course, at speed v. So we looked at this the other day, that we know the speed of this object is given by this expression here. And we know that the gravitational potential energy of the MM system, or the two-mass system, is given by this expression here. So what we can actually do is we can look at the energy contained, or the energy, the energy of this satellite. So the total energy, again, is going to be kinetic energy plus gravitational potential energy. And remember, the only force acting on this satellite is gravity at this point, so we don't have to worry about any other sort of types of energy. And so if we just kind of sub in some of the values we know this is our value for kinetic energy. This is the value for gravitational potential energy. We do a little bit of subbing in for our value for speed from up here. So we're just going to kind of take this value and put it in here. And we end up with a pretty cool expression if we do some manipulation, do some algebra. And we come up with this expression here. The total energy of this object is just given by this, which, if you remember, is only half the gravitational potential energy. So what that means is the total energy of any object in a circular orbit is given by just this pretty simple looking expression. So we can tell a whole lot about a satellite just by the masses and its height. So we can actually tell the total energy, which then again, if we want to, we could actually go and figure out the kinetic energy. And again, we didn't really constrain ourselves to many things here. The only thing we really constrained ourselves was to the idea that we only have these two objects, and that we also constrained ourselves to the idea that this is a circular orbit. We'll talk a little bit later on about how we can generalize this for ellipses, and it's really not that difficult. And you might be surprised how simple it is. But anyways, so this is true for any object in any circular orbits. So that's a pretty profound result if we've actually found this. But what we can actually do is then we can look at it and say, okay, well, what if the object, just isn't in orbit? What if the object just kind of traveling around this mass? So I have some other object flying by in space. What sort of things could happen? And really, we want to look at the total energy to get an idea what that's going to look like. And we actually have three different cases for the total energy of an object. Of course, it shouldn't be too surprising. The options are negative, 0, and positive. But what's really neat is that we can make a lot of conclusions just based on the sign of the energy, the total energy for whatever object we're talking about here. So just for simplicity, let's for right now just constrain ourselves. So we're only talking about the Earth as the parent object. So this would be the object we're measuring things relative to. So this would be like the things that something might orbit around. So if you have negative energy, that means the object, of course, total energy is less than 0. But what this means is the object is bound to Earth. So we're going to use that term that if something is bound or binded to another object, that it's kind of stuck. And what that means is we can have this thing move around inside of Earth's gravitational field, but unless we give it more of a push, it can never leave. Because remember, from our definition of potential energy, we said that gravitational potential energy goes to 0 under what conditions? Well, it's as we get our separation approaching infinity. So the only time we can have negative energy, which means if our total energy is actually less than this 0, which means we never have enough energy to leave Earth. So again, without extra work, without extra energy, this object will never ever leave Earth, Earth's gravitational field, I guess I should say. And so it's kind of bound or stuck here. And so an example might be a satellite. I'm going to jump down to something with 0 energy, exactly 0. Not about, but exactly 0. And so it's kind of the opposite of negative in terms of the fact that it's not bound to Earth. So it has enough energy to escape Earth's gravitational field. But this is a pretty special case because, yes, it can get out of Earth's gravitational field, But when it's infinitely far away, it has no kinetic energy. So this is like that perfect amount of energy. It's just enough to get away, and then once it's gone, it will be stopped. So there's no more energy for it. So it's like the exact perfect balance of energy. So this generally doesn't happen in nature. We don't normally things have with exactly zero energy. But so negative, the other option, of course, is positive. So like zero, this object is not bound to Earth. But the difference here is that even when it's infinitely far away or it's far enough away from the object we consider the GPE to be zero, it's still going to be moving. It's still going to have positive kinetic energy. And so this means this thing will never ever come back to Earth unless another force acts on it. So it'll just take off and be gone. And so an example of this is the Voyager probe. It's a pretty cool idea. I don't know if you've ever heard of the Voyager probe, but it was launched way back in the 70s. And again, it's the furthest human-made object ever to, well, ever from Earth. And it's recently just left what's now considered the edge of the solar system. So now it's in interstellar space. That happened just, I think, last year or the year before. So anyway, so this object has positive total energy, will never come back to Earth unless something else pushes it. And it's probably not very likely in interstellar space that that's going to happen. All right, so these are our sort of three cases. There's not really any other options, but if we look at these, we actually have some other ideas. So if we look at an object that has less than zero total energy, so that means if I go back to this page here again, so something with a negative energy, what that actually means is we have to give that thing extra energy to escape the gravitational field. And we're going to call that extra energy, the additional kinetic energy, the binding energy. So it's how much of a bigger kick would you have to give something in order to kick it out of the gravitational field. So to give you an example, if we have a 200 kilogram satellite, it's orbiting Earth at this altitude, what is its binding energy? And so remember, for a satellite traveling around, the total energy is just given by half the gravitational potential energy. So again, I can kind of leave that as an exercise. It's not very difficult. But you come up with the total energy being this. So there's the total energy the satellite possesses. But before we go any further, again, remember what this means is, what does this total energy mean? It means that if the satellite, let's say, let me draw my little graph here. We're graphing here energy versus separation. If, as we go to infinity, the energy goes to zero, this thing can get out. And if it goes to not zero, or below zero, then we can't get out. So what this is saying, this has this much energy less than it needs to escape. So its binding energy is just going to be the positive version of that, because I have to add this much energy to this total energy to make that equal zero. So I can say like this plus this equals zero. So this is the amount of energy I have to add to the satellite in order to get it to escape Earth's gravitational field. If I added less than this, what would actually, this would actually be kind of interesting. Let's say I added 6.24 by 10 to the power of 9 joules. So just less than what it needs. What would actually happen if this satellite would, this satellite would get almost out of Earth's gravitational field, would get very close to escaping, but just as it stops, it would still be there, and it would slowly then fall back to Earth. And if I give it just more than this, it would keep traveling forever. It would never stop. The only way I can give this, if I give this exactly 6.25, it would travel just outside of Earth's gravitational field to the point we could say it goes to zero, and it would come to rest. So again, as I said, this represents the total energy must be added to the satellite to get it to escape Earth's G-field. Okay, so that's kind of the idea of binding energy, and something that's kind of related to that is escape energy and escape speed. So the only difference between really escape energy and binding energy is escape energy, we're limiting ourselves to something that is not moving. So how much kinetic energy do I have to add to something that's not moving? Or how much kinetic energy in total does something have to have in order to no longer be gravitationally bound? So if I've got an object sitting on one another, so let's say I've got a rocket sitting on the Earth, which I'll do down here in a second, I need to know how much energy do I have to add to this to get this rocket to escape. And that means, again, have zero total energy and never come back to Earth unless another force acts on it. And a related idea is this idea of escape speed. And this is how fast would an object need to travel to get that mass to leave Earth's gravitational field and never come back. So that's the idea of escape speed. So let's just go through this example here then. So I've got, in this case, a rocket, and it's resting on the surface of the Earth, and I have to know how much energy do I have to add to this to get it to escape Earth's gravity. So we know it's at rest, so that means the only energy we have to be concerned about is gravitational potential energy. So here is our gravitational potential energy. Whoa, that's crazy. Expression. And then I slid the numbers in. Of course, this is the mass of the Earth. This is the mass, pardon me, of the rocket. And right now we're going to use r being the radius of the Earth because we're on the surface, right there. And remember, the radius is measured from the center to center. So we have this potential energy of 7.5 by 10 to the 10 joules. And again, what that means is, in order to get this, this rocket to escape, I have to have this much total kinetic energy. And we're going to call this the escape energy. And again, you might be asking yourselves, wow, this sounds very similar to the idea of binding energy that we just did back here. But notice in this case, this object was already traveling at some speed, and this one was traveling at no speed. Or the other way to think about this is that we don't have to necessarily add this energy if it's already moving. This just tells us the total kinetic energy it needs to be able to escape Earth's gravity. So that's the escape energy. And if we look at the escape speed, as I said here, it's the minimum speed we have to project this mass from the surface so that it's no longer stuck to Earth. And so we're going to do this one. Let's bring this closer to home a little bit. And we're going to figure out your escape speed right now. So you're sitting probably at home or in school or wherever the heck you are watching this video. And what speed would you have to be traveling at right now to escape Earth's gravity and never come back? So if we start with, again, we know the escape energy, I've given it ESC down here, is equal to the negative of the gravitational potential energy, because I want to take this energy, add it to this energy, and get to 0. I want to have just enough energy to get out. So the escape energy again here is just given by this expression, since you're not moving, you're sitting still, hopefully, or close to it. And so this would be your the energy you need to escape, and the energy form this will be in is kinetic. So what we're going to do is say the kinetic energy equal to escape energy, and that means our kinetic energy has to be equal to this expression here. Do a little bit of rearranging, and I want you to notice something kind of neat here. I'm going to actually right here, yep, that the mass, your mass, actually cancels out. So this is a pretty cool result. What this means is that no matter how big an object is, I need to launch it at the same speed to get it to escape Earth's gravity. Of course, it's going to depend on the mass of Earth, but it won't depend on the mass of the actual object that's doing the escaping. And I think that's pretty neat. So that means I'd have to launch you at the same speed as I would a rocket. So again, I think that's pretty neat. So we keep rearranging this expression now. So v squared, and we solve for v, and we get that the escape speed is just depending on the mass of the object, in this case the Earth, and r, how far away from the center that object is. So we plug in the numbers for Earth, and we actually get this quite fast speed, around 11 kilometers per second. So what that means, sort of, if you wanted to jump and escape physics, jump off the surface of the Earth or wherever the heck you are right now, you'd have to jump at 11 kilometers per second straight up. And of course, we hopefully realize that that's an incredibly fast speed in terms of day-to-day life. But most objects that leave Earth, like for instance a rocket or the Voyager probe I just talked about, they don't have that speed right at liftoff because they're actually being powered on the way up. The assumption we've made here is that once you're jumping or being flung off of Earth, that there's no more extra energy being added. And so for things like rockets, that's not true. So they are certainly powered after liftoff. Okay, so again, with this idea in mind, we can talk about this pretty cool idea of a potential well. And so what I've got here is a graph of the gravitational potential energy. Don't worry too much about the units, but the higher the scale, of course, the higher the gravitational potential energy. And we've also got the distance away from Earth in terms of kilometers. So the further away you go from Earth, of course, the gravitational potential energy increases in the system. But let's pretend that, for instance, you have, we'll do a couple different scenarios here. Let's say you start here at just off the surface of the Earth, so maybe this is a satellite orbiting, and this is the potential energy. So if it's the potential energy and it's a satellite orbiting, it might have total energy somewhere up here. Let's say it's up here. So here is the kind of total energy representative of this system. Oh, sorry, I just noticed one thing, and maybe you picked it up already, that um, this graph actually uses a different sort of scale than we do. Well, maybe not a scale, but a different zero. So our zero, of course, would be at this r equals infinity. So this would be zero. These should all be negative, but that's, sorry, just a sidetrack there. We kind of, no, that's fine. All right, so again, so here's our potential energy of our satellite, but it has, I don't know, 20 megajoules per kilogram um, of kinetic energy. So what that means is actually if I somehow shoot this satellite so it goes straight away from the Earth, it would actually travel quite quickly up to here. It would stop here, and then it would start falling backwards. So it's kind of stuck or trapped in this area here. It's bound to be forever in this area. It can go below this distance away, so it can go closer to Earth than, ooh, that's a terrible line, closer to Earth than this line, but it will never go past that line. It can go below here and go fast, be right here and stop, but it will never go past here unless we add some extra energy. And again, I think this is kind of neat, and this is where that name potential well comes from, just from that idea that it looks almost like a well when you fill it in, that the further away you go, the more energy you need. And so if you only have this much energy, you're stuck and you can't get out. And so that's that term potential well. And of course, if I have infinite distance to begin with, I can actually travel anywhere along this well. And we say that you can actually escape this potential well, or you have enough escape energy to actually get out. Your binding energy in this case would be, what do you think? 0, because you don't have to add any extra energy to get out because you already have enough. All right, so let's take a look at another kind of cool aspect, though, the thing I promised at the very beginning of the lesson today, black holes. And this is actually something pretty cool because you now have enough physics to really understand the basics of what a black hole is. So if I go back actually to this potential well picture, I hope you can agree that if this were a more massive object, so if the Earth were more massive, this would be a deeper sort of well. We'd have to extend these lines further out, and it would take more energy to escape the gravitational field. So what we do for a black hole is we imagine we make this object so massive and so compact, so small, that actually the escape speed becomes the speed of light. The speed of light, again, is that theoretical maximum speed for any massive object to travel at. And so if we have an object that's so compact and so heavy that its escape speed is the speed of light, nothing will ever escape from that distance, from that r, that radius here. And we call that radius the event horizon. That's the closest anything could possibly get, according to this idea of light being the fastest object, and it would never ever be able to escape. There is no speed fast enough that's physically possible for this thing to actually escape the gravitational field of the black hole. So it's like it's an infinitely deep potential well, almost infinite in terms of that nothing that can actually travel can escape. And we can actually determine the minimum radius that a black hole would need to be just by setting the escape speed to c. So we use our escape speed and we set the escape speed to c, and we're going to call this radius the Schwarzschild radius. I believe it's a German scientist who was one of the first guys to really work with Einstein's relativity equations. And so we get this pretty simple looking expression for how big a black hole, or sorry, how compact an object would need to be in order to produce a black hole. And all it depends on will be the mass. The rest of these things are constant. So that, again, is something kind of neat. The only thing that determines whether an object is a black hole or not is its mass and how compact it is. So to kind of put these numbers in perspective, let's take a look at a common object, so the sun. So again, how small would our sun, and here's the mass of the sun, need to be in order to form a black hole? So it's, again, just plugging the numbers into the calculation, so I won't go through it with you here. But the result is about 3 kilometers. And that's pretty crazy, that if we wanted our sun to be a black hole, all of the mass of the sun would need to be compacted into an area, so the radius is around 3 kilometers. And again, to put that in perspective, from CKSS to Jean Vanier, just down the road there, it's about 3.5 kilometers. So the entire sun would have to be compacted into an area about the size of Milton in order to form a black hole. So certainly very compact, but that also speaks to how dense black holes must be, just because of how fast light can travel. So again, that's pretty much it on me for today. I hope that, again, you found this pretty easy to follow, and certainly pretty exciting. Some cool stuff we talked about.